You can deal with the issue problem with it. You can deal with the issue problem with it. What is that? You're in class, my God.
No, I don't think that was my own bath one. No, because I didn't want to
Okay.
But it wasn't.
Turn it on. You can make sure to turn it on. You can turn it on and
Okay.
You read all three of them, yeah?
that's right. You can turn it on, didn't you?
That's like on Thursday, not over there. You read like day ones as well, yeah?
Yeah, all three, like.
That's what I got on Thursday after
New assistant, something.
the former student, yeah. Sounds like we're having a day. Well, later on this day.
I suppose overloaded or
First one best.
Good morning, ladies and gentlemen. Last lecture we started with synchronous logic. We stopped at designing a simple up counter. We followed the typical synchronous sequential concept. So our state register, in front of that, the calculation of the next state, and with the feedback path, and our output logic. The schematic symbol and RTL diagram reflects that using these clouds, and the typical function shown here. We already modeled it in VHDL. We used current state and next state of type unsigned, because we could easily perform some arithmetic operation just in incremental, what we need here for our next state logic. The usual state register here, and finally the back conversion using a typecast or type conversion from our current state of type unsigned to standard U logic vector, because the output count O in the entity was declared of type standard U logic vector. I think we stopped here, right? Any questions? Then, consequently, we want to verify if our model really works. As usual, our entity, our empty entity, our test bench architecture, which makes our counter visible, to use it in a component instantiation of, or as a module under verification. What we introduced last time was, because we are dealing with synchronous logic, the clock generation process. So please fill in the clock generation process. one way how to write a clock generator using this process. Actually, it's the same what we had in the falling edge detector design previously. To perform a verification, we need a verification plan. It starts always with activating an asynchronous reset and deactivating the asynchronous reset. Hence, another line of code is necessary for the reset. So our reset signal underscore RST underscore NI gets assigned an initial reset of 0. Comma, now you can use a comma separated list. Actually, it's also a concurrent statement, and tell the system it should assign a 1, but with a keyword after, for example, the constant period. The first, yes, please.
Sorry, just why is it period over 2 again?
Why a period?
Yeah, over divided by 2 instead of just period.
This period?
The one above, why divided by 2? Is it just because there's the two of them, or?
Okay, the period, the clock period, for example, is declared here as 10 nanoseconds, and if we want to have a square wave, 50%
right,
duty
okay.
cycle, then we can easily provide it in that way.
Gotcha. Thank you.
Following the verification plan on the next page, in our stimulus process, we wait until the asynchronous reset settled. So there is a wait statement here, wait until the reset is 1. And after that, we activate an enable, wait for a full counting cycle, activate the enable, done as usual, we just assign a 1 at the enable input. Then we wait for 15 times period because we're expecting our counter counting from 0 to F. And then we could use an assert statement to check if the count value is F. So again, this means, this assert statement means if count under O is not F, you have to read it in that way. Then report it using this string, expecting the count F, which failed, and a severity failure here. Then wait for another 5 periods just to check that the enable works. So after 5 periods, wait another 3 periods and activate the enable again, wait for another cycle, and then if you count consequently, then we should get a 3 because we have our enable introduced, which kept our counter waiting for some cycles. And finally, switch off the clock generator by setting clock enable to false, wait, and exit. And if you look at the simulation result, you will find something like, here is our first part, the reset. Then we activate our enable after that. During the reset, the count initial value was 0. If we activate the enable, the next rising edge starts and continues counting until we have an F here. Then we waited another 5 cycles. Then we switched off the counter for some cycles, switched it on again, and let it run until the end of our verification plan. Okay? Actually, verification is an important aspect where designers are working heavily together. So different designers, I mentioned it before, write the model, other designers write the verification according to some verification plan. Because on your own you don't find your mistakes. Of course not in the simple case of an up counter, but much more complex situations we have. The prototype test environment, also very important. We want to know how fast is our counter, how many lookup tables does it need, how much chip area is used for our design, as always. So the central element of device under test will be put on the prototype environment, typically our DE1 board with a Cyclone 2 FPGA. We connect the clock input to the clock oscillator, which is directly on board. We connect one of the keys to the asynchronous reset so that we could press an asynchronous reset. And of course, we can also use another key to the enable input to switch enable on and off and check that. So what is missing here actually is not line up connection here. We could connect it to our binary to 7 segment encoder and to a 7 segment display to see the result, to see it counting, but then we have to think about that. And we have to think about our 50 megahertz clock, of course. But what I wanted to show you is what is the result if we look at an RTL viewer. So let's use our virtual machine. This is our design environment. The DE1 count up enable uses the clock signal, the key, which is a vector of 2, 1 for the asynchronous reset as mentioned before, and 1 for the enable, and the hexadecimal display at the moment. We need to introduce or make visible 2 components. One component is our binary to 7 segment encoder, and at least our counter. Then we assign the different signals, the clock 50 megahertz to our clock signal, key 0 to our asynchronous reset, and the enable to P1. We instantiate our device under test with the signals which provide our counter output, and this goes to our binary to 7 segment encoder. The next step is we go to our place and route environment, select that, open a terminal, and just type make RTL view. Then our Quarters backend tool from Intel should start with a graphical user environment. And here you can use the RTL viewer, for example. Double click on the RTL viewer, should provide us with a kind of a block diagram on a block level. So it should be similar to what we have in my script. The count up enable drives the binary to 7 segment decoder. We could dive into the blocks, just you see the cursor changes. It's a kind of a symbol which tries to make that there is a hierarchical component and there is more hierarchy levels below and there is an arrow going down. So you can just double click to go into the next level. And the next level is, as we expected, just our state register, our next state logic cloud, and our output logic cloud. If we click on the logic cloud, we could see, or it tells us, hey, there is an incrementer here. Just an other implemented, and if you look at the second, zooming in, it tells us the second operand of our other is just a constant 1, 4-bit wide hexadecimal 1. That's notation, as we expected. Okay. There is another viewer which is called technology map viewer. Typically, when we run through the different steps, which we normally do not using the graphical user environment, we are doing that with a makefile, because normally designers do not work with these graphical user environments, just in special situations. So if we go through the different parts, analysis and synthesis, and then the fitter, the so-called place and route, where the elements are placed on the chip. Actually, in an FPGA they are already placed, so there's a kind of routing necessary here. Then after that, Quarters, our backend tool, knows exactly how many lookup tables are used to implement our design, and it will provide us with this information. We could use also this technology map viewer. We always get a report here. Very similar to the RTL viewer, but now you can see it introduced a special element, which is a clock control driver already on the chip. Lots of clock control drivers are available, and we have dedicated input pins to connect it to that. The designers of the prototype environment used that. And again, we can go one step below inside the counter. Then we see a more an example which is more or nearer the technology of the FPGA. And you can see for a 4-bit counter, we should, instead of this state registers where the 4 flip-flops are behind each other, so stacked, here we can see the individual flip-flops. Current state 3, 2, 1, and there should be 0. In the usual way, we know from basic digital electronics how to design a simple up counter. Additionally, you see the logic cells here. So it uses a logic cell for the combinational logic part for the first flip-flop, another logic cell for the next flip-flop, another logic cell, and so on. You remember maybe that the arithmetic will getting more and more complex from stage to stage. At the beginning, it's very simple. If we dive into this lookup table, it will tell us, hey, it's just a simple XOR with an inverter on one input. If we go into the next element, it's getting a little bit more complex, but we leave that actually to the compiler to find the equations. And here it tries to visualize what is inside these boxes, and so on. Okay? So some lookup tables are necessary, a special amount of lookup tables. How can we find a summary of that? If we close that and look at the total logic element, it tells us we need 12 logic elements here. And from the 12 logic elements, we need 4 registers, something what we expect actually. And how many percentage of the pins are used, how many percentage of the total memory multiplier PLLs are used, so all the components also available on the chip, which helps us designers to find out how complex our design will be. Okay? And if the other parts will fit on the chip as well, which we have to design, depending on our specification. So that was a short demonstration about the prototype environment. Also on my slides here. If you do not have any more questions concerning the counter and the design of this very basic synchronous logic element, then I will continue with the next basic logic element, a shift register. A shift register always needed because nowadays we transfer data, we work on parallel data, we have to serialize data to transfer it over different communication channels, and we have to receive the serial data and parallelize it again. The central key element actually is a shift register. A serial parallel converter, parallel serial converter. This would be the typical application for this shift register. Very simple, it just uses logic elements of D-type flip-flops. And if you could or would look like in the same manner as we have next state logic, state register, output logic, then the state, next state logic are just wires. And the output logic as well. So very simple. Actually, what we have here is to connect these outputs. Very often the designers do just right here. We have a 4-bit output vectors. So actually we do not connect something like that, that we connect every output to this bus. Could be done, but nobody does it. So we connect by name, not by wire. So this is clear for all the designers. The same here, so we just say what the names of the clock or the reset signals are. We do not connect it here. Because at the end we would get more and more wires and can't identify the modules we are looking on. Okay? Let's have a look at the behavior directly using a simulation result here. There is a serial input data stream and a serial output data stream. The serial input data stream is just 0, 1, 0, 1, and then always at the clock edges, so 0, 0, 0, 0, 1, 0, 1, 0. And this data stream is shifted in to the serial data input. And we see it at the serial data output and at the parallel data output. Actually, the LSB is shifted first. So if we consider this 0, 1, 0, 1 combination at the beginning, you can see after 4 clock cycles, it is shifted in and seen at the parallel output. So this is then the LSB, and this is the MSB. Then we shift in 4 zeros, and vice versa, 1, 0, 1, 0. And these 1, 0, 1, 0, you should have at the end, again after 4 clock cycles, here and here, the MSB and the LSB. So LSB is shifted in first. Here or here. And at the end, you can also see that this is the result at our output, at our serial output. Let's look at a VHDL model. The usual entity uses clock and reset, serial in, serial out, parallel out, all standard U logic, but the parallel out is our 4-bit output vector. In the schematic above, I used D and Q for inputs as usual to the flip-flops. Therefore, I declared these internal signals D and Q also as 4-bit vectors. And we can easily, after begin, just write our first approach on how to write our next state logic or state register. So let's start with the state register. I use a label here and use the vector Q is, just for simplicity, initializing it with a reset. Sorry, when reset is a 0, else it gets the value D when there is a rising edge on the clock signal. So stick to the template for the registers. Yes,
This is
please.
a typo, how to reset equality.
Where do you think is it?
That being equals, not an assigned.
Oh, therefore, that one, yes. If you look at the schematic again, we just have to describe wires. So the first wire is D3 gets the value of the serial in. D2 gets the value of Q3. D1 is Q2, and so on. So D, element 3, gets assigned the value of the serial data input. D2, index 2, gets the value of the output, which is Q3, and so on. So we are nearly finished. What we need to assign is our serial output. It's just Q index 0, and the parallel output just our vector Q. So just connecting wires between the elements. But I have to admit, this is not the style VHDL designers do it. Think about a 64-bit shift register nowadays. Okay? I think you could easily find out that there is a regularity here. D2 is just the following element, Q3, D1 is just the following, Q2, and so on. So instead of writing that, I just move that down. We could also write a vector D2 down to 0 gets the value of Q, index 3 down to 1. So I can comment these lines. Then we reduce that to 2 lines, getting the input value of serial I to the first bit of D3 and the rest just a kind of shifting connections. Okay. Another possibility would be to include the serial data input as well. So if we would like to write D3 down to 0 and include the serial data input on the left side, so we could write serial I, and now make use of this concatenation operators introduced in the language fundamentals. Remember the shifting, and write Q of 3 down to 1. Then we can also use that and comment the first line. So having 1 line for the next state shifting step. Actually, additionally, because D3 down to 0 is our vector, we do not have to write the range of the vector. We could directly write D is, the full vector is just serial data input shifted into the NSP and then shifting further on 3 down to 1. So at the end, only 4 lines of code. The state register, the next state logic, if we say here, this is our next state logic as a label. And these 2 lines as a comment are our output logic. We still follow our synchronous logic block design. So again, 3 blocks. Last optimization, we could directly include the state logic, the next state logic, in this case, into the state register. So we could also write the state register and just copy that part for D. Then we have just our state register, which includes here the shifting, and finally provide the output signals. But in these simple situations where it is really very clear how the model works using a simple shift register, I would use that. But normally we have more complex situations, therefore we always try to write it, the model as transparent as possible for our colleagues. So carefully think about putting lots of information into one line of code. Actually, I would recommend that one. So have this one as the state register, this one as the next state logic, these two lines for the output logic. Okay, think about your colleagues who have to maintain your code segments. Anything else? No? Didn't forget anything. The simulation result I started for the behavior of the, actually you know that there is an end missing. Okay? So just to make it complete, of course, there is an end here missing. RTL. To have the complete architecture. The simulation environment, very similar. Again, uses the component ports, our usual constants, instantiates our shift register. For the shift register, needs a clock process, needs initialization of our reset, and starts with a stimulus process for waiting on the reset to settle, and then we provide a serial input data stream. So 0, 1, 0, always wait a period in between, then check the parallel output. So actually here we would write something of an assert statement, which I leave to you. What do you expect at the parallel output O after these 4 serial inputs? Then, as in the simulation result, we inject 4 zeros here. Again, check for the parallel output. Then vice versa, 1, 0, 1, 0, check the parallel output, wait for 4 periods, and switch off the clock generator and suspend the stimulus process using the wait statement. How can a shift register be used to model something what is called a pseudo-binary sequence generator? A very common building block used in digital electronics. So see the details. on Wikipedia, for example. File name linear feedback shift register. Just a few words about the terminology. It uses the 4-bit shift register we modeled before. Additionally, instead of an input signal for serial data, it introduces a feedback path. And these feedback paths, there are different possibilities. Just one, for example, is depending on where we connect our feedbacks using XOR gates. And depending on these XOR gates, we get different patterns, output patterns at our output queue or as a serial data stream, which we call noise, pseudo-random noise at the output. So this feedback path is often an exclusive OR, but can also be an exclusive NOR. These are called taps. Depending on where the feedback gates are connected, where it is included, on which taps, there is a dependency on what kind of output data stream is produced. There are different possibilities to realize that. One is called Galois linear feedback shift register, the other is called Fibonacci LFSR. And what else? Yeah, that one, for example. At the beginning, you can see, therefore I used it in red. So to initialize our shift register, normally we have our asynchronous reset. But if you calculate the results, you will find out if we initialize at 0, so at the outputs 0, 0, 0, 0, the next state will also 0, 0, 0, 0. Therefore, we would have something like a wrong color. So if we start at the output 0, 0, 0, we would always get back to the state 0, 0, 0, 0. Okay? Therefore, we have to start with another state, and one possibility is to start with a 0, 0, 0, 1, a 1 at the LSB, which means we use a set instead of a reset for the V-type flip-flop for an initialization. So please think about that all the connections from the reset are to the asynchronous reset, but the last, or the LSB one, to the set input. And then we can start with a 0, 0, 0, 1 at the beginning. So Q3, Q2, Q1, Q0. We could write the function of each. So B3 would be, for example, just B0 X or, sorry, not D, Q0 and Q1. And D2 is Q3, D1, like our shift register, Q2, and D0, Q1. So these are our equations for our linear feedback shift register. If you remember our XOR function, the behavior of our XOR function 0, 0, 0, 1, 1, 0, 1, 1, we get a 1 if both are unequal. Just to remind you that. So what is the next value starting from 0, 0, 0, 1? What will be the next values of Q3, 2, 1, and 0 according to these equations? So Q3, Q2, Q1, Q1, these are just shifted, as you can see here. Right? So we can just write or do something like that. Okay, so we get 0, 0, 0 here, and D3, which is calculated, and then after one clock cycle produces the result at Q3 is calculated using these XOR function. XOR Q0 and Q1. Unequal, so we have a 1 here. Doing the same here. We have 1, 0, 0 here. Again, XOR function. Is 0, 0, okay, this is a 0. And so on. So if you write the hex value, you could write 1, an 8, 4, a 2, and so on. Or using a state diagram, we will start at 0, 0, 0, 1. And the next brings us to 1, 0, 0, 0. And so on. So if you start little reset here. And at the end, it should go back to the beginning. And depending on what we call this function, this equation, depending on where the XORs are in the tabs, these 4-bit shift register can produce what we call a maximum cycle. It goes through all possible values beside that. The applications are, for example, for fast counters where we do not want the count result as usual in the usual way of counting up, counting down. We're just interested in the counting or something for the communications systems to scrambling and descrambling input data streams, and or in cryptography for cyclic code, CRC, cyclic redundancy checks. It's a typical way to do that. And here is the way how to write that in digital electronics. And the same modeling styles we used before, based on the shift register, we can use for our LFSR4. Additionally to clock and reset, and we introduced an enable signal here. Our actual parallel data is called LFSRO. Our serial output data we call noise because it's a serial data stream which is pseudo-random. And we could also provide a signal which tells us this is the end of the cycle, like an up or down counter which counts modulus, where we provide a terminal count signal at the end. Okay? So I named the architecture Fibonacci because I would like to model it according to the Fibonacci model of an LFSR. Here I introduced an attribute mentioned before. So instead of writing 3 down to 0, I used this attribute length and used LFSR length, which calculates 4. It calculates the length of the vector LFSRO. Then I calculate -1 and get a 3 down to 0. Start with a state register. How would you write the state register? Just by using the templates we used before. So state register should not be a problem following our pattern. Additionally, introducing our enable signal, don't forget to consider that. Okay. Parallel output, easy. Just write LFSR-O and assign the value of Q. Yes.
Why go to the trouble and using the LFSR length when defining the signals? When in the state registers we again use a fixed length register.
Just to show you how to use the attribute. Okay. So step by step I'm trying to introduce you more and more elements and modeling. Of course, in that case, just writing 3 down to 0 would be sufficient. Even not as long as. Okay? But normally we will have LFSR register length of 24 bits or 36 bits, 32 bits if you look at some standards. Actually, there are some standards about maximum cycles of linear feedback shift registers. Serial out, again, also very simple. So our noise output instead of our serial data output we previously had, just another name is just the LSB of Q. The next state logic, sorry. Our shift register, so D2, down to 0. It's 3 down to 1. And the feedback introduces actually our D3 value. This is just a simple equation we wrote before. Q1 XOR Q0. Wrong here. This is the serial output, of course. And the end of cycle signal we introduced in the entity, the end of cycle. How would you write that? It should produce a 1 when our Q is equal to our initial state. Just a simple output logic. In all other cases, it should provide a 0. So let's have a look at the simulation environment. The usual parts, including component instantiation, clock generation, initial reset, starting with the stimulus process, which waits on the deactivated reset. We can directly go to assigning the enable signal a value and activate the generator, and now waiting for a full cycle. So 4-bit values, so 4-bit LFSR means it has a maximum cycle of 50. So we could just wait for 15 times period, or we could make use of another statement, wait until there is, for example, a rising edge of our end of cycle output signal. Which you could never do or are never allowed in writing a VHDL model. Never ever write such a statement. Wait on a rising edge on any type of signal. You are only allowed to write rising edge of clock. Okay? Otherwise, you would violate our synchronous design rules. But in a test bench, you could write anything, what you want. Introduce files, introduce pointers, what you want. As long as it meets your requirements. Okay, therefore, I'm waiting on a rising edge, or I could also wait on the falling edge. Considering that, okay, there must be a 1 for 1 clock cycle, and at the end, it will produce again a 0, so I could also wait on the falling edge of the end of cycle. Okay? Waiting for another 2 periods, for example, just to see the end of the simulation. So these results of our end of cycle. Therefore, I introduced another 2 periods here. Nothing really spectacular here. We have our enable started here and enabled all over the time, so we didn't check actually the enable. So the verification plan is not complete for this linear feedback shift register. We do not verify here that the enable really works. Okay? Our LFSR outputs, we can see here, are starting with our initial value 0001, then with an 8, with a 4, with a 2, with a 9, and so on. Producing these noise, these serial data stream here, pseudo randomly. And at the end, producing our end of cycle here. Do you have any questions? Then I would like to summarize what we discussed. The fundamental storage element of our synchronous logic is the D-type flip-flop or the D-type register. Mandatory design rules. Think about all of our synchronous logics. We have one shared clock. No combinational logic allowed on clock path. The reset is never gated through additional logic. So very important, never gated. We can easily model our n-bit shift register, n-bit registers using our conditional signal assignments or when else statements. Always use the rising clock edge in our situations of a clock signal. Never use rising edge on another signal. We considered an edge detector. One approach how to model an edge detector using the two flip-flops and an output logic, so the two flip-flops and the output logic, using a combinational output logic function. We introduced the synchronous counter, simple up counter, which uses all the design pattern used so far for the state register, and then for combinational logic for the next state logic and also the output logic. The shift register as a main building block for serial, parallel, serial conversion. How to write that using very few lines of code. And at the end, our linear feedback shift register, which we need very often to produce pseudo-random noise in different applications all over. Again, my question, do you have any further questions considering this topic? Because then I'll give you, because Friedrich is here, the last 10 minutes a possibility to discuss individual questions with us directly in front of your computer, of your virtual machine you may have at the moment, which we can use the last 10 minutes, and then we see us tomorrow same time. Okay? Thank you for your patience.
See the exams of writing out this code. See the exams of writing out this code. Is there any past papers for this exam? Has anyone got one?
Really weirdo. You didn't even tell weirdly.
Did any of you go on past papers for this class?
No, not yet. A few.
Oh, look at how he draws an infinity. It's
Look at how you draw yours, Vincent.
Why? What's
Right.
infinity? Can you do an and symbol?
Do it 8. Draw an 8.
Oh, I love it when we answer.
Draw an 8?
Yeah, draw an 8.
Actually, Kevin does
the
the
same
right
way
way.
as him.
Kevin does the right way. See,
Why? What's wrong with that?
that's the right way.
I do like
He does.
Why? What way do you do it?
He does it.
Oh, you go the opposite direction?
Yeah.
Yeah, so does
He's just like a
Ivan.
freak.
Oh, but apparently I do my sixes like a left-handed person.
Oh, you
Oh,
do.
that's
serial
weird.
killer. That is.
No, this is
That's apparently how
weird.
left-handed people do it.
Hold on. What I do?
Oh, you do
weird. I do
yeah.
this.
No.
Yes.
I do from the top line.
From the top
Yeah,
down.
same.
Middle.
And
These are
because-
same?
and because I do
So
my
out of
sixes that
curiosity,
way,
draw
it
an
makes sense.
infinity. I want to see if you keep the direction consistent. Oh, you do? Okay. Interesting.
Do that symbol. Can you do that?
Oh, I can't. I don't know how to draw them. Like by automatically.
Right,
Like I don't
Chris.
know.
Right here's what I'll say. Right, you do. You say you do your sixes like this, yeah. From the top down, yeah.
Yeah.
So it only makes sense to do your eights in the same direction.
Except I'm back as well.
Except the way you write, whenever you write a letter, right? You try to write the letter so it ends going this direction. Whenever I finish my 8, I'm ready to like hop back this way again. Though so are you technically, I guess.
Yeah.
But yeah, so
What way do you do
I
your
don't know,
8
it just
start?
feels very
Where do you start?
like I can end the
Where do you
flick
start?
and continue. So if I want to write
Oh,
eight,
you start from where you draw.
you're the same. Interesting.
When you draw a star.
This is a
Yeah.
conversation
Star?
we've gotten into before, like last semester.
Dancing
what
was
way did you
important.
start?
I don't really. I don't
Where
have
do you
the.
start?
I don't have the in my muscle memory.
Oh, the arms really fuck. Yeah.
It's a useful
So what
tool.
way do you do it?
Start from the tail.
Start from the
You do your. Oh, you do your arm different. Yeah, I did mine like this here.
So if I had to guess, like
Oh, you do yours differently. I start
it
like,
would probably be like my 8 to be honest in terms of
basically.
I did mine from the bottom.
You
like
start
that.
from the outside and then you go.
I did. Yeah, like that there.
But that wait, do that again.
I did like that. And then if I'm doing it with treble clef.
It's hard for me to draw. I like.
Treble clef go again.
I can't. So like,
Oh, that's weird. Could you draw that like your 8?
it's upside down. Eight.
Oh, yes.
Yeah. It's like my
Yeah.
eight.
There we go.
Oh, see, that's like drawing your 8. That's what that feels like. Oh, that's cursed.
Well, that's what it looks like.
It is what it looks like. Enjoy your travel class. I don't need it. How do you draw your pound sign?
I don't know.
From the top
Oh,
down.
Yeah, I do like that.
That's a dollar.
No. Like, you know, the classical.
Oh, you do like that. I just do mine like
Oh,
straight lines.
do you just do like the fucking this
Like
way?
I do that. Yeah.
That's fair.
Oh, the 2 ticks is a dollar, is it not?
that's what I thought. That's why I only do one tip.
Yeah, I always go. Don't know, dollars this, Pete?
Yeah, that one's too big.
What am I thinking of then? Oh, it's the 2 ticks.
The euro.
Yeah, that's the
Oh,
Euros.
yeah.
The Euros circle, bomb. My pound signs used to look like Euros. 'Cause I used to try and do the one you'd see in the shop.
One time for me, because I'm not going to this year.
Lucky bastard.